Right, here we go. Question here about a magnet being attached to a spring, and we're going to oscillate it, and then we're going to change the amplitude of the magnet's oscillation and see what happens to the current. Okay, so let's have a look at this. This is quite a nice one because it combines two areas of physics. We're looking at SHM and electromagnetic induction, which is quite a nice combination, as you can see. Now, for this one, we've got our original signal. This is I0 and T. We want to compare that with the new signal. I think a good place to start first is to look at the period. You'll notice here in A and C, the period is different. Okay, in B and D, the period is the same. So I think we're going to try and identify which of these we should get rid of first. We're going to do that by thinking about our SHM. We've got a mass on a spring. Okay, it's a magnet, but it has mass, and therefore it's going to go with T equal to 2 pi over times the square root of m over k. Now, why have I put that in? Well, what have we changed here? We've changed the amplitude. The amplitude is not present in this equation, so we can get rid of those answers which change the period because the period doesn't change. So A and C are going to drop out here. Now, the next question is, how do we compare these two? Now, we notice here we've got the same amplitude here, okay, and we've got a lower amplitude here. Well, why is this important? Let's evoke another equation here. Our maximum speed goes with omega x0, and so therefore actually if we decrease that amplitude, we're going to decrease the speed. Why is that important? Well, if we apply our Faraday's law of induction, we know that the EMF, or the current, is going to go with the rate of change of the magnetic flux. And so therefore, if our object is generally moving slower, we're going to induce a lower current, which means having got rid of A and C, we're going to get rid of B, and the answer here is D. Lowering that amplitude lowers the speed and therefore lowers the rate at which this is changing, and thus the current going through the coil.